Good morning. Now that we've learned how to find maximum and minimum points on any curve, it's time to apply that in the solution of some word problems. So I'm going to go through some examples with you. These are right from exercises 24.7 from your textbooks. And the first problem here is number 8. It says, if an airplane is moving at velocity v, the drag d on the plane is d equals av squared plus b over v squared, where a and b are positive constants. Find the value of v for which the drag is the least. Okay, so we want the value of v that minimizes the drag. Okay, determine v such that d is a minimum. Okay, so that's what we're trying to do. Determine v such that d is a minimum. Okay, now you have to remember how we located minimum points on a graph. What we did was we took the first derivative and set it equal to 0, and then we solved for x. So we would do the derivative of y with respect to x is equal to 0, and then we solved for x. Well, what we're going to do here is the derivative of d with respect to v. So we need to find the derivative of d, treating v as the variable. So in order to do this, we should rewrite the equation av squared plus b times v to the negative 2. So we have to rewrite the function so that v is not in the denominator. And now we can take the derivative of the drag with respect to the velocity. So remember, the a and b are constants in the problem. So they're just treated as numbers would be treated. So this will be a times 2v. Right? A times 2v plus b is multiplied by negative 2v to the negative 3. So this is the same as 2av minus 2b v to the negative 3, or 2av minus 2b over v cubed. Okay, so that is correct for the first derivative of the drag with respect to velocity. Okay, so again, we treated v like the variable that it is. A and b were treated like numbers. Okay, so this is what we set equal to 0 now, because we are looking for a minimum. So remember, that means you take the first derivative, set it equal to 0, and you solve for the variable little v. And after that, we'll also perform the second derivative test. Okay, but we're on this part now. We're going to set this equal to 0 and solve for the velocity. Okay, to solve for the velocity here, a little trick we can use, now that we have the left side equal to 0, we can multiply all terms through by v cubed to the denominator. And this will get rid of the denominator. So this will stay 0. This will be 2av to the 4, and this will just be 2b. So we multiplied all terms by v cubed. And now we're trying to solve for v, so we'll isolate it. So 2a v to the 4 is 2b. And that would, of course, be the same as a times v to the 4 is b. V to the 4 is b divided by a. And so then how do you find v? You take the 4th root. So v is equal to the 4th root of b over a. So now we've executed this part of the solution as well. So that's the correct velocity. And now how do we ensure that we have found a velocity which provides for a minimum? Well, we would do the second derivative test. So we're going to take the second derivative. You could just write this capital D double prime if you prefer, but this is the correct way to say the second derivative of the drag with respect to velocity. And we will evaluate it at this velocity here and ensure that it is positive. Remember, when the second derivative is greater than 0, we have a minimum. So these are the 3 steps required in the solution of the problem. So let's go ahead and find the second derivative. So the first derivative expression that we're going to use is this one here, okay? If you try to use this one, you'll end up starting by bringing this term up, right? So this is the one that we should use if we're looking to differentiate again. So now, treating v as the variable, the derivative of this term will be 2a times 1. And the derivative of the second term will be negative 2b multiplied by negative 3v to the negative 4. So what do we get? We get 2a plus 6b v to the negative 4, or 2a plus 6b over v to the 4. So that's our expression for the second derivative. And in particular, we want to evaluate it at this value of velocity. Okay, now look, in our actual equation, we have v to the 4. So it would make sense to just substitute b over a right here. So we can say when the velocity is this, the 4th root of b over a, then v to the 4, remember, is b over a. And the second derivative is 2a plus 6b over b over a. So that's the same as 2a plus 6a, and it is 8a. How do we know that 8a is greater than 0? Because in the original problem, they said a and b are positive constants. Okay, so all of this part here is called the second derivative test. And all we were doing is ensuring that at the velocity we found, the drag would be a minimum. All right, so that's a first example, a little bit challenging because of the constants a and b. I'm sure you would have found this question simpler had there actually been numbers here, perhaps a 2 here and a 3 here. Then you would have found the question much simpler. Okay, but we'll do some more examples together now, okay? So let's go on and try from the same exercises. This one here is problem 19. So problem 19 says, A rectangular microprocessor chip is designed to have an area of 36 square millimeters. What must its dimensions be if its perimeter is to be a minimum? Okay, so let's try this problem together. I think we should begin with a diagram. All right, essentially it should be a rectangle that we're drawing to begin with, okay? So let's do that. Do a quick sketch here. All right. Okay, so that's my rectangle. We're trying to figure out its dimensions. So that means we actually need to label the dimensions on here. So what I'm gonna do is say that these dimensions are called X and Y. Okay, so there's my rectangle. Now, what do we know about this rectangle? We know that its area is 36 square millimeters. So we should be able to write an equation based on that picture and that fact. So what is the area of this rectangle? It would be X multiplied by Y. So now we know that X multiplied by Y is equal to 36. Okay, let's continue to read. We're trying to find the values of X and Y. We're trying to find the dimensions. The perimeter is to be a minimum. So we need an equation for the perimeter. So what is the equation for the perimeter of this rectangle? Well, perimeter means the sum of the four side lengths. So X plus Y plus X plus Y, or 2X plus 2Y. So that's the perimeter equation, and that is what we're trying to minimize. So this time, what are we trying to do? Find X and Y such that P is a minimum. Okay? So we know how this is done. This means taking the derivative of P, setting it equal to 0, and solving. But one issue we have here is that currently this equation has two different variables in it. X isn't constant, Y isn't constant. We have two variables in it, so we can't take the derivative yet. So what we're actually going to do is eliminate one of these variables. And we can do that because we know that the product of the two variables is 36. So for example, from this top equation here, I can write that Y is 36 divided by X. And I can now substitute 36 divided by X right here for Y in the perimeter equation. So now it will look like this: 2X plus 2 times 36 over X, or 2X plus 72 over X. And that's much better because now we have a perimeter equation with only one variable. So this means, what can we do? We can take the derivative of that perimeter equation with respect to the variable X. We can set it equal to 0, and then we can solve for X. Okay, so this is like what we did in the first question when we wrote sort of our game plan over here on the side of the page. So I'm going to execute this now. I'm going to take the derivative of this. with respect to x and then set it equal to 0. Now, just like the previous question, we have to rewrite this first if we intend to take its derivative. Okay, so we rewrite it like this. And now we can do the derivative of perimeter with respect to x is, here the derivative will be 2. And then here, so we have plus, and then this will be negative 72x to the negative 2. Okay, so 2 times 1 plus 72 times negative 1x to the negative 2. So we have this now, or this as our correct derivative. What do we do with it? We set it equal to 0 in an attempt to solve for x. Okay, so in order to help us out, we can use that little trick again. We're going to multiply all terms here by x squared. So 0 is 2x squared minus 72. Solving for x, so first we can isolate 2x squared. It is equal to 72, which means x squared is 36. X is the square root of 36, and x is also positive, so x is 6 for this question. We do have units provided, so x would be 6 millimeters. All right, now that we have x, remember we're trying to find the dimensions, both dimensions, so we can find y very easily. Remember, the area of the rectangle is 36. So if x is 6, y is also 6, right? Y is 36 over x. So x is 6, y is also 6. So x is 6 and y is 6. And so, in fact, the best way to minimize the perimeter is to make the rectangle a square. Okay? Lastly, we should include the second derivative test. So what does that involve? Take the derivative again. Okay, so this is p double prime. This can be written p prime, p double prime. And if we're looking to ensure that we have found dimensions that will minimize the perimeter, then we're looking for the perimeter to be a maximum when x is 6 millimeters. So let's include this portion of the solution. So our first derivative was right here. So what will our second derivative be? Well, the derivative of 2 is 0. And then for this part, the negative 2 comes forward, multiplies by negative 72 to give us 144 x to the negative 3. So we end up with 144 over x cubed. And when x is 6, the value will certainly be positive. It's 144 divided by 6 cubed, which is exactly 2/3 or 0.6 repeated. We don't really care about that number. We just care that it is a positive number. Okay? So once again, we needed to have a perimeter equation that involved only one variable. Then we were able to take its derivative set it equal to 0, and solve for that one variable. After that, we performed the second derivative test. Okay, we will try another one now. Okay, so we're gonna try. This is problem 25. I'm trying to avoid the sun. Sorry. There we go. It's like a bit of a battle, really. No, that's not good. Oh no, I'm gonna go right there. All right, here we go. Question 25. A computer is programmed to display a slowly changing right triangle with its hypotenuse always equal to 14 centimeters. What are the legs of the triangle when it has its maximum area? Okay, we have a right triangle with a hypotenuse of 14. So I will begin by sketching that. Okay, so a quick sketch. This is my triangle with a hypotenuse of 14. Okay, what are we trying to find? The legs of the triangle. So again, the two other side lengths. So we need to call them something. So X and Y. Okay, so in the last question, we had a rectangle labeled X and Y. Now we have our triangle, base and height, X and Y. All right, so what are we trying to do for this question? We are trying to maximize the area. So we're trying to find X and Y such that the area is a maximum. And at this point, we should probably write down what we're going to use for the area equation. Okay, so what will be an expression for the area of this triangle? Well, the area of a triangle is 1/2 the base times the height. Okay, so now we know that we are trying to find X and Y such that A is a maximum. Find X and Y such that A is a maximum. Okay, now just like the problem we finished, problem 19, the issue is we cannot yet take the derivative of this because it contains two different variables. So as we did in the previous question, we have to replace one of these variables. In the last example, I replaced y, and so I'll do that here as well. But what do I replace it with? We need an equation from this triangle that links X and Y. And hopefully you know that this would be the Pythagorean theorem. So for this triangle, x squared plus y squared is 14 squared, or 196. So from this, why don't I isolate y? So y squared will be 196 minus x squared, which means that y is the square root of that. Okay, And yes, you are stuck with it in this form. You cannot split this. It is not equal to the square root of 196 minus the square root of x squared. So in other words, this is not the same as 14 minus x. Okay, you have to keep that binomial like it is underneath the square root sign. Okay, you can only split a radical if it's multiplication or division, not if it's addition or subtraction. So we're stuck with this, okay? So anyway, let's go over here and rewrite this. So we're replacing y with this square root of 196 minus x squared. But since I know I'm going to be doing some derivatives, it might be wise to write it this way with a fractional exponent instead. Okay, so now I'm going to execute the plan. So the plan is we're going to take the derivative of that area with respect to x. We're going to set it equal to 0. And right after that, we're going to solve for x. Now look, the question has here, omit the second derivative test. Actually, that's something that I added. We're not going to perform the second derivative test when it's going to be ridiculously complicated algebra. So we're going to skip that. And so all we're going to do are these two steps. Take the derivative of this with respect to x, set it equal to 0, and then solve for x. Okay, so let's get started with our derivative. Now, this is a function of x, right? This is a function of x, and they are multiplied together, 1/2 base times height. And so for the derivative, we are going to have to use the product rule. So we have u multiplied by v. Let's write down what we're going to be using both for u prime and v prime. Okay, u prime is pretty straightforward. The derivative of 1/2 times x is 1/2. Now what about v prime? Well, v requires the chain rule. So the half comes forward. The new exponent is -1/2. That's, of course, 1/2 minus 1. And don't forget, you have to multiply that by the derivative of the inside of the bracket. The derivative of the inside of the bracket is 0 minus 2x, so -2x. So v prime is, we can take a half, multiply it by -2x to get -x there. Okay, so now we have u prime and we have v prime. A reminder that we use the chain rule to differentiate v. And so now when we're writing down the derivative of area, we have to use the product rule. Do you remember how that goes? That's uv prime plus vu prime. So u times v prime plus v times u prime, like that. Okay, now let's simplify this a little. So this becomes -1/2 x squared in front of this guy. Oops, 196. Can I just squeeze? Like that. And here, let's put the half in the front. Okay, so we could common factor this, or we can handle it a little like we did the first two questions instead. Okay, but the key, of course, is going to be that we set this equal to 0. So I'm going to set it equal to 0, and I'm also going to write it now with square root signs. So that we can treat it like we did the previous 2 questions, okay? But as I said, if you prefer, you can use common factoring in this step instead. Okay, so a little bit of an explanation here as to what I did. So I kept the -1/2 and the half just sitting in front of each term. And now here, this had a negative exponent. So it drops down so that it's under x squared. So it would be x squared over 196 minus x squared to the positive 1/2. And so that exponent of positive 1/2 gives you the square root sign there. Here the exponent wasn't negative, so that's why this square root is not in the denominator. It's just, you know, if there was a denominator here, it would be 1. Okay, so now we're going to use the tricks that we used in the last examples. For example, we can multiply all of the terms by 2. Let's start with that. And then that would look like this. Okay, so the first thing I did was I just multiplied these terms by 2. So we don't have -1/2 here anymore, we have -1. And we don't have a 1/2 here anymore, we have +1. And now let's multiply all of the terms by this very denominator. So we're going to multiply all of the terms by the square root of 196 minus x squared. So of course this will stay 0. This will become -x squared. And here, when you multiply this by itself, you get 196 minus x squared. Okay, so again, we multiplied all 3 terms here by, and maybe I'll write it down, multiply by the square root of 196 minus x squared. All terms. Okay, and we got this. Well, that's kind of cool because this now simplifies to be 196 minus 2x squared. If we just collect these 2 like terms here, the bracket serves no purpose because the coefficient in front of it is 1. Now we can solve for x. 2x squared is 196. Therefore, x squared is 98. And x is the square root of 98. Okay, and that is roughly square root of 98. Okay, so there. Oh, boy, have I been writing off the page this whole time? Jeepers. I'm going to have to go over that with you, right? So the square root of 98 is roughly 9.90. Okay, so we used the product rule right here. And then at that point, I simplified here, -1/2 x squared in front. Here I put the 1/2 in front. I went to the form using the radical sign here. Then I multiplied all of these equations by 2, and that gave me this form. And I did that, of course, to get rid of the denominator of 2. Okay, so you can see that that was what happened. That then made this coefficient -1 and this coefficient 1. Then we multiplied all three terms by the square root of 196 minus x squared. And when you do that here, when you multiply by the square root of 196 minus x squared, you'll just get negative x squared. And when you multiply this thing by itself, you will get 196 minus x squared. That's, you know, the same as if you had square root 3 times square root 3, you get 3. Collecting like terms here, I get 196 minus 2x squared. Solving for x, so isolate 2x squared first, divide by 2, and then take the square root. And this would have units equal to centimeters. And then once you know your value of x, it's the square root of 98, we can then find the corresponding y value, because remember the Pythagorean theorem holds. So y is the square root of 196 minus x squared, or 98. So y is also the square root of 98. So it also is roughly 9.90 centimeters. So what did we find out? We found out that this right triangle will have these two side lengths equal. So it's actually an isosceles triangle. So the conclusion is that if we want a maximum area in this case, we would make sure that the triangle is isosceles. So the base and the height are equal in our right triangle. Okay, so again, the algebra was a little tricky here, so maybe I'll just run through it one more time, because I apologize, I think the page was being cut off while I was going through the steps. So this is the product rule. This is the simplified product rule. Again, this is just rewriting the product rule, but with a radical sign. All right, and then I used the tricks that I used in the previous two questions. So first, I doubled all terms. That eliminated this denominator. And then to eliminate this denominator, we multiply all terms by it. And that is where the real magic happens, because look how simplified this is. From there, the problem became easy to solve for both x and y. Okay, so I know this isn't a terribly easy topic. It's going to certainly take a little bit of practice. I am going to stop our video right here, because any longer and you might lose focus, and certainly it'll take a long time to upload if it's any longer than this. But I will be doing a second video. I'm going to go through 2 more examples with you in that next video. Okay, great.